Hey guys, this is the last video for section 5.3 dealing with related rates. The one problem left in your notes is about a man walking with a spotlight shining on him. So I've got kind of the similar same thing. I've got a plane flying with a spotlight focused on the plane. So don't worry about what's going on in the problem. Don't worry about the numbers, the speeds, anything. Just watch the picture and look at how the measurements are changing when this plane starts to fly across the sky. Let's talk about what's changing. The plane's distance here is changing because of this. The plane's distance, not this distance, the 4,000, but the distance from the point closest to the light to where the plane is, that length is changing. This isn't changing. This angle is changing. Okay, so here's what's happening in this problem. The plane is flying at a certain speed, okay? So this x is changing at a consistent rate, constant rate. And this isn't changing. The angle, however, is changing at a different rate according to where the plane is. So right now, this is in radians, 18, 17, 6. I can't count that fast. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. You see how my counting sped up? I was just following the radians. So when the angle is small, the angle's changing very fast. But the bigger the angle gets, the slower that the angle changes. And that's what we're going to be looking at is, hey, how fast? So if we freeze him somewhere, like stop. Nope, stop. When we froze him, how fast was that angle changing? Or maybe out here. Ready, stop. How fast was that angle changing? That's what we're trying to do in this type of problem. Okay, so we got a man on a path with a spotlight. Doesn't matter which direction you start your man traveling in. It really does not matter. So we've got a path. I'll make that the path. And I'll draw a man. Man walking along the path. And there's a light focused on him. There we go. Light focused on the man, and as the man walks toward our right, the light's going to follow him, so that when he gets here, the light would be like this, right? That's the setup. Now, let's start translating from wordy to mathy. So here we go. A man walks along a street. Oh, we got a rate here. The man's rate on the path is 4. His speed, he's traveling this way, his speed is 4. So here, I think this is what's happening. Hang on, let me keep reading. Searchlight is located on the ground 20 feet away from the path. Okay, I'll go ahead and put that there. 20 feet from the path. Got it. 20. Kept focused on the man. We know that. At what light is the searchlight rotating? I'll come back to that. when the man is 15 feet away from the point on the path closest to the light. That's the best way that they can come up with the wording to say when his distance from here is 15, okay? So this is where he's closest to the light. He's walking away from the light. When his distance gets to 15, that's what we want to focus on. So, he's walking along a straight path at a speed of 4. I think I'm going to make X represent his distance from the point where he was closest. He's going this way, so I'm going to call his distance traveled X. And thus, I can say X is changing at a rate of 4. So dx dt is equal to 4, right? I knew I needed to write this as a rate of something. I just need to figure out what I'm going to call it, what it represents. So it represents the distance from here, wherever he is along the path, and that's changing at a rate of 4. Searchlight, got that. At what rate? Find. At what rate is the searchlight rotating? Oh my goodness. So here's what's happening. It was on the man. The man's walking, so the searchlight has to be turning, right? Here's what it's asking. How fast is this angle changing? So I need a name for the angle. I think I'm going to call the angle theta. It's the angle that the light makes. It's asking how fast is theta changing. Find the rate of change of theta with respect to time. At the moment that he's 15. So when that distance is 15. Now, something to point out. A couple things to point out. This length right here is changing. This length is not changing. This length is changing, but it's never mentioned. It's kind of irrelevant. This angle is changing. So what we need to do is we need to come up with an equation that involves this measurement, not the derivatives yet, but I need to come up with an equation that involves x and involves theta. And heck, while we're at it, we can go ahead and use the 20. What kind of equation can you think of that involves an angle and this side of a right triangle and this side of a right triangle? It's tangent. So the equation that I'm going to start with looks like this. Tangent of an angle is equal to opposite over adjacent. Okay, hold on. I just put a number into my original equation. Is that legal? No, unless it's a constant. This is not changing. You may use it right now. This is changing. You may not use 15 right now. This is changing. You may not use a value for it right now. That, you're only allowed to plug in values after you do the derivative. Like when we're pretending that everything's moving and we're going to freeze time for just an instant. Okay, so knowing that I'm getting ready to do a derivative, it might help you if I write it like this. Just put your 1/20th as a coefficient, maybe. Because if you don't, some of you are like insistent, I'm going to make calculus as miserable as I can. If I didn't rewrite it, some of you would be goofy and try quotient rule. That would be awful. Okay, so I did a quick rewrite. Now, keep in mind, theta is changing. It's messy. Time is my variable. X is changing. It's messy. Time is my variable. So whenever I do my derivatives, and whenever I encounter a theta, whenever I encounter an x, I've got to remember to chain rule it. Here I go. I wish you all were out there for me to pick on somebody. Oh, dang. So the derivative of tangent is secant squared. Don't forget to chain rule it. Keep your constant. So the derivative of 1/20th x is just 1/20th. However, x was messy. Don't forget to chain rule it. Okay, we have a value to plug in for dx dt, so that is 1/20th times 4. D theta dt, that's what we're trying to find. And, oh golly, we've got some work to do to come up with secant squared of theta. So just for a minute, I'm going to write this as smart as you all are, some of you get kind of confused when it says secant squared. Here's what that means. It means I don't need the angle. I need the secant fraction for the angle so that I can square that fraction. Okay? You don't need to find the angle. You need to find the secant fraction for the angle. And if you don't like that, if you don't want to find the secant fraction, okay, then find the cosine fraction. Because then we'll just flip it upside down. So, let's work on this, getting this fraction to put in here. You ready? Let's go back up to our picture. So remember, we're like freezing. We're like stopping, moment in time. When are we freezing it? We're freezing this situation when x is 15. So if I put a 15 up there, do you think that you all could come up with a cosine fraction, because cosine and secant are reciprocals of each other? Do you think you can come up with a cosine fraction for theta? I think you totally can. Cosine is adjacent, got it, over hypotenuse. Oh, no big deal. You can do Pythagorean theorem, or you can recognize that you've got a triple here. I know your triple the triple that you like to think of is like 3, 4, and 5, right? Did you all know that every multiple of this triple is a triple? My measurements in this problem are 5 times bigger than the triple that everybody has memorized. So 15, 20, and 25 is a multiple of 5 of the Pythagorean triple that you all already know. So according to the Pythagorean triple, this would be 25. Now, you can make your cosine fraction. Your cosine fraction is adjacent over hypotenuse, so 20 over 25. Don't be ridiculous. Reduce that. Holy moly, reduce that. So my cosine fraction is 4/5. Ready? That means the secant fraction that you will insert in here is 5/4. And I reduced this over here too. So basically what we've got is we've got 5/4 and 5/4. I'm going to have to invert and multiply. So I get d theta dt ends up being 1/5 times the reciprocal of that, which is 4/5, 4/5. Nothing wrong with that. Okay. Just want to check and make sure I was right. It is 16/125. So that's the rate at which the angle is changing. Now we need units. Put units on there. I just found the rate at which this angle is changing, 16/125. Totally did that without a calculator. It wasn't that bad. Now, y'all could have made it 10 times worse. Y'all could have tried a quotient rule here without thinking ahead and trying to make your derivatives as simple as possible. Some of you refuse to reduce fractions, and then you would have to insert the fraction, and then you would have to, divide. Oh, some of you just make calculus as miserable as possible. There are ways to make it simpler. Always look to make it simpler. Anyway, radians. What are angles measured in? Angles are measured in degrees and radians, but guess what? Calculus doesn't work in degrees. So it's always going to be radians. So this would be radians per second. Radians per second. There you go.